Today's my lecture topic is small gas turbines. Many small gas turbines which produce below 5 megawatt are designed similar to the large turbines already discussed. However, there are many designs that incorporate centrifugal compressors or combinations of centrifugal and axial compressors as well as radial inflow turbines. A small turbine will often consist of a single-stage centrifugal compressor producing a pressure ratio as high as 6:1. A single-side combustor where temperatures of about 1800 degree Fahrenheit are reached. The radial inflow turbines in a typical turbine, air is introduced through an inlet duct to the centrifugal compressor, which rotating at high speed impacts energy to the air. On leaving the impeller, air with the increased pressure and velocity passes through a high efficiency diffuser, which converts the velocity energy to static pressure. The compressed air contained in a pressure casing flows at low speed to the combustion chamber, which is a side combustor. A portion of the air enters the combustor head, mixes with the fuel and burns continuously. The remainder of the air enters through the wall of the combustor and mixes with the hot gases. Good fuel optimization and controlled mixing ensure an even temperature distribution in the hot gases which pass through the volute to enter the radial inflow turbine nozzles. High acceleration and expansion of the gases through the nozzle guide vane passage and turbine combine to impart rotating energy, which is used to drive the external load and auxiliaries on the cool side of the turbine. The efficiency of a small turbine is usually much lower than a larger unit because of the limitation of the turbine inlet temperature and the lower component efficiencies. Turbine inlet temperature is limited because the turbine blades are not cooled. Radial flow compressors and impellers inherently have lower efficiencies than their axial counterparts. These units are rugged and the simplicity in design assures many hours of trouble-free operation. A way to improve the lower overall cycle efficiencies 18 to 23% is to use the waste heat from the turbine unit. High thermal efficiencies 30 to 35% can be obtained since nearly all the heat not converted into mechanical energy is available in the exhaust, and most of this energy can be converted into useful work. These units, when placed in a combined heat power application, can reach efficiencies of the total process as high as 60 to 70%. In aeromotive, this unit has 3 independent rotating assemblies mounted on 3 concentric shafts. This turbine has a 3-stage axial flow compressor followed by a centrifugal compressor, each driven by a single-stage axial compressor. Power is extracted by a 2-stage axial flow turbine and delivered to the inlet end of the machine by one of the concentric shafts. The combustion system comprises of a reverse flow annular combustion chamber with multiple fuel nozzles and a spark ignited. The aeroderivative engine produces 4.59 megawatt and has an efficiency of 32%. Thank you.